Welcome back to CST432. Today we will start taking the first step into the ARM assembly language programming proper. So we shall get started with the ARM assembly language programming for the next. As mentioned previously, native programs for the next are based on the ARM assembly language instructions. ARM instruction set is relatively simple yet powerful. Now, as we go through this module, it's good to keep a copy of the ARM and Thumb2 instruction set quick reference card QRC0001 UAL, which is a reference in the end of this slide, end of this presentation in the notes page with you for reference. Now please bear in mind too that only the ARM v4t architecture instructions are present in the next microcontroller. The reference card contains instructions for more advanced versions of the ARM controller, which we will not be using. Some of the key concepts we will cover in this module are the instruction format and usage, some assembly language programming examples, and finally, flow control and how it affects the implementation of algorithms. As we go through this module, there are some questions that you might like to keep in mind. First of all, in a typical CPU, why are there different instructions for subtract and compare when they both implement A subtract B or A compare with B? Secondly, in ARM, instructions can be executed conditionally. What is conditional execution and why is it useful? We will first look at data movement instructions. The first use of data movement instructions is for register access, of which we can use it to initialize values into registers or to transfer, which is actually a copy of contents from one register to another. The second use of data movement instructions is to transfer values from memory into registers or from registers to memory. First, we look at the register access instructions. Here you see the MOV or move instruction highlighted in the slide. The optional suffix S controls whether the status flags in the status registers are updated or not. So in this instruction, we have a destination register RD and followed by the operand 2, which is the value that we want to put into RD. So the purpose of the move instruction is to copy the value specified by operand 2 into destination R sub D. Now, operand 2 uses what is termed as addressing mode 1. It is quite flexible. It can either reference an immediate or constant value, but please take note it has to come from a restricted range. Otherwise, it can refer to a register, or finally, it can refer to a register value that is modified by a bit shift or rotate of that value before it is copied into the RD register. Here we look at the operand 2 format in more detail. The first version, which refers to a constant value, we must prefix operand 2 with a hash and followed by the numeric value itself. Now this constant or immediate value has to have an 8-bit size, meaning that the start bit and the end bit must all fit within 8 bits range. And this value actually is scaled, meaning that it doesn't have to be only 0 to 255. For example, we have a move R1, comma, hash 0x AB00, which is actually an 8-bit value shifted by 8 bits to the left. The second operand format for referring to registers will only specify the register as the operand. So in this case, it's actually equivalent to register sub M shift left by 0 bits, which doesn't change the value in register M. So for example, the use of MOV R1, R7 is copying the value in register 7 into R1. The third version, RM, bit shift operation and a constant hash value for the number of bits to shift given by I allows us to have a fixed bit shift operation to convert the value of the register M before it is copied. Example of this is move R1, R2, LSR hash 8. So what happens here is that the register 2 value is shifted right by 8 bits before it is copied into register 1. Final version allows us to have a flexible or variable bit shift. So we specify the number of bits to shift in a register R sub S. So example of this is move R1, R2, rotate right or ROR, and using the value or number of bits to shift in R3. Here we look at some more concrete examples of register access. The first instruction, move R0, 0x, FF constant value, is a valid move instruction because it loads the value 255 into R0 and the bit span of this constant fits into 8 bits. Second instruction, move R7, 0x, 008, 00000, loads the value 8388608 decimal into register R7. This is valid because the bit span of this value, constant value, again fits within 8 bits. The third example, move R0, 0x, F8, 00300 is not assembled by the assembler because the bit span of this constant exceeds 8 bits. Consequently, the assembler, when you encounter this statement, will generate an error and refuse to compile or assemble the program. The fourth example, move R0, 01FE, again cannot be assembled because the bit span of this constant value cannot fit into 8 bits. The fifth example, move R3, R0, LSL #2 is an example of using a bit shift operation on the register R0, which allows us to multiply the value in R0 by 4. We'll study a bit more about multiplication later on in this module. The next example, move R9, R1, ROR, R2 allows us to specify a variable number of rotate positions in the register R2. And finally, we have the example of RRX as an optional operand to operation on register R2. Now, there are two instructions, MRS and MSR, which allows us to manipulate the status register in the processor. So MRS will copy the value of the processor status register into a register RD, whereas MSR will copy the register of constant value into processor's the status register, but we have to specify the fields of the processor that we want to update. We can either update the value using a constant immediate 8-bit value, or else we can load the constant value into a register first and then copy it into the status register. Of course, these two operations are restricted to privilege mode because the status register is privileged. So when we want to specify the status register, we can either specify the current processor status register or the safe processor status register. The fields within the status register that we can specify include C, X, S, and F, which are controlling the byte of the 32-bit value that will be updated. Here we look at the processor status register in more detail. We see that the control bits are from bit 0 to bit 7, include the mode bits and the interrupt and state bits. The status and extension bits in the PSR on the ARM4T architecture is not defined, it is reserved, so we will not cover those. Finally, the flags bits, or the from bit 24 to 31, include the condition code flags, which are used for determining the current state of the processor after an arithmetic or logic instruction or compare instruction has been executed. Here we look at how we can implement a few simple initialization of registers. In this case, we are interested in initializing register 0 to 30 hex, register 1 to 180 hex, register 2 to -1, which is a signed value, and finally register 3 to 65536 decimal. First of all, we encounter in assembler directive .global. This defines the starting address for the entry point into the program, which is in our case start. The first instruction in the sequence is MOV R0 #0x30. We can do this because the value that we are interested in fits within 8 bits of the bit span. So by doing move R0 hash 0x30, we have initialized R0 to the given value. The second instruction is to initialize R1 into 180 hex. Now we can do it two ways. We can either load the constant value 180 hex literally into R1, or in this example we note that 130 hex is actually a shifted version of 30 hex. So we will make use of the value in R0, left shift it by 3 bits position, and then store the new value into R1, which gives us 180 hex. Next, we will load the value -1 into R2. Note that in this instruction, we add the suffix s to the move instruction. So move s will initialize the flag register or update the flag register to indicate that it is a negative value, or the end flag will be set. Next, we want to initialize R3 to 65535. Now in hexadecimal, it is FFFF in the lower word of the lower half of the word. In this case, we will make use of two instructions in using instruction synthesis style to implement this initialization. First, we use the MVN or NOT of instruction to convert a 0 constant value into all 1 bits, and that FFFF value will be stored into R3. Then we will shift it right within the register by 16 bits. When we do a right shift, logical shift right, or LSR, the most significant 16 bits of this register will be set to 0. Remaining bits are shifted right until only FFFF remains in the register. So finally, after these two instructions have been executed, we are left with FFFF hexadecimal, or else it's equivalent to 65535. Finally, we come to the branch instruction that causes the program execution to continue forever on the stop instruction. Next, we look at the memory access instructions. These are LDR and STR, load and store. And load and store uses addressing mode 2. There are various variants of load and store, whether it's referencing to byte, half words, signed byte and signed half words, which uses addressing mode 3, which is actually similar to addressing mode 2, except that the range or different versions are more restricted. Now we can use load and store to access to arbitrary constant values stored in memory location known as a literal pool. A literal pool will be accessed by using the equal symbol to prefix the value in the operand. So for example, load LDR R0 equal OXABC 123 DE will load the value, constant value, from memory into the register such that R0 contains the value in hexadecimal of ABC 123 DE at the end of this instruction. Now, addressing mode 2 is for indirect addressing. In this case, we are using addressing mode 2 to specify register Rn as a pointer. When we use it this way, the value of Rn is unchanged. So we have three different formats for indirect addressing using Rn. The first version is square bracket Rn, comma, hash, and a constant value, whether it is positive or negative. This offset value will be added to the register contents of Rn before generating the address that we are accessing in memory. So one example is LDR R1, comma, open square bracket, R3, comma, hash 4, which will load R1 from memory, the word located after the current word addressed by R3. Meaning the address that we are referencing in memory is not the address given by R3, but the word which is 4 bytes away from the current address. The next format is Rn, comma, plus or minus, followed by R sub m. Okay, this allows us to have a variable or register-based offset, and the offset can be either forward or backwards in memory from the current address pointer Rn. Example of this is store R7, R2 minus R5. Okay, this will store R7 into memory at address given by the value of R7 subtract the value of R5 to give us the actual address. The next format is Rn plus minus Rm and followed by a bit shift operation with a constant offset, constant bit shift value. This allows us to scale the value in R sub m by a given amount. An example of this is LDR R1, R3, R4 LSL #2. Now if we set value in R4 register 4 to 1, this will be equivalent to the first instruction we looked at, LDR R3 open square bracket LDR R1 open square bracket #4, which is 4 bytes away from the current address given in R3. The next way we can use addressing mode 2 is what is called pre-incremented pointer addressing. This means that the value in Rn is updated before accessing memory. The format is similar to the previous version that we studied earlier, except that we append the exclamation mark symbol to the end of this addressing mode 2 expression. So in this case, when you use Rn, hash plus minus constant offset, close bracket, exclamation mark, what we will do is that we will update the value of Rn before accessing the memory location. Right, so for example, LDR R1, R3 #4 exclamation will load the address location of the word after the current address location in R3. However, if we execute the same instruction again, LDR R1, R3 #4 exclamation again, this will actually increment or advance the pointer to the next word position. Okay, so if we execute the same instruction over and over again using the pre-increment pointer addressing, this will move from one memory location to the next memory location within memory. Now the next version of this, of course, is Rn, plus minus R sub m, close bracket, exclamation. This allows us to have a variable offset to update the address pointer. And finally, we can also modify the R sub m with a shift operation specified by a constant offset, a constant shift value. So again, an example given is LDR R1 open square bracket R3, R4 LSL #2 close bracket, exclamation. The last version of addressing mode 2 is called post-increment pointer addressing. This is somewhat similar to the pre-incremented pointer addressing, except that the R sub n is updated after accessing memory. So similarly to the other case, when you execute the same instruction multiple times, you will change the value of the address pointer and you will access the different memory locations the subsequent times when we use the same instruction. So the format for specifying post-incremented pointer addressing is by using the address pointer register in the square bracket by itself, followed by either the constant offset, the variable register offset, or the scaled variable register offset, as given in the examples in this slide. Finally, we have the swap instructions, which are used for atomic memory access. So the swap SWP instruction, RD/RM square bracket Rn, allows us to perform a 32-bit word swap between the contents of memory in Rm is stored to memory address given by the pointer R sub n, and the value in R sub n will then be retrieved to R sub d. The other version, swap byte or swap SWPB, only stores an 8-bit value. Now the operation is non-interruptible, meaning that when we are performing this exchange of data between Rm, memory, and Rd, no other instruction or interrupt can take place and affect the operation. Consequently, it is used as a mutual exclusion or semaphore primitive. The last group of memory access instructions are the vectored memory access using load multiple and store multiple. Now, load multiple and store multiple requires a mode qualifier. This specifies the direction and sequence to update the base register R sub n. The exclamation symbol is used to optionally update R sub n after the completion of the load or store multiple sequence. Finally, we specify the list of registers to load or store into memory or from memory. And these combination are used very often for accessing to the stack in memory. Here we will look at an example of how memory access is performed. In this example, we will go through the sequence of manipulation from A, B, C, D all the way up to K several times using different options or combinations of memory access instructions. So basically what we will do is that we will initialize the stack pointer to 0x5200 hex, and then we will store value of 83 hex into memory address location 4000 hex. Next, we will then push the registers R0, R3 to R3 into the stack. We will next load the word stored in location 1000 hex into R0 and the word stored in location 1004 hex into R1, and we will then swap these two values and such that location 1004 hex now contain the value of location 1000 hex, whereas location 1000 hex contains the value in location 1004 hex. We will repeat these steps D to G using the scaled register offset example, and then we will repeat it again using swap as an example, and using swap with one register only, and finally we will terminate the program by removing the contents of R0 and R2, R3 from the stack back into the original registers. The first step in our program is to initialize the stack pointer. This is important because the stack pointer allows us to store and retrieve temporary values into memory in the last in first out manner. Next, we will store the constant value 83 hex into memory. We do this by first initializing R0 with 83 hex constant value. Next, we need to use register R1 as a memory address pointer, which we initialize to 4000 hex to refer to the memory location at 4000. Then we will store the value in R0 into memory given the address pointer R1. For the next step, we will be storing some values R0, R1, R2, R3 into the stack to preserve them before we continue execution of the rest of this program. We use the instruction STM for store multiple, FD for full descending stack. So using the stack pointer SP as the address pointer, we will store the registers R0, R1, R2 and R3 given by the register list in the curly brackets into memory, and finally the stack pointer is updated using the exclamation mark symbol so that the stack pointer now points to the top of stack. Now we see how we can perform the memory content swap operation. The first step is to load the address pointer to address 1000 hex into register R3. Next, we will use the post index addressing mode to load the contents in memory at location 1000 hex into register R0, after which we will increment register R3 by 4, constant value 4, which points to the memory address 104 after this instruction has completed. Subsequent to that, we can now use R3 as the address pointer to address location 1004 hex to load the value from memory into register 1 for temporary storage. After we have loaded the two variables from memory into register, we then swap them by storing the contents of R0 into memory address location pointed to by R3, which contains the value 1004 hex currently, and then we decrement the value in R3 by 4 using the post-index addressing mode. This will cause R3 to then change its value back to 1000 hex. And finally, we store the value in register R1 into the address location 1000 hex using store R3 store R1 square bracket R3. Next, we will repeat the swap operation using a scale register offset approach. First, we initialize register R2 with the constant value 1, which is the size of the scaling. Then we do LDR R0, R3 again, which allows us to load the value from address location 1000 hex into R0. Next, we use LDR R1, open bracket R3, R2, LSL #2, close bracket, to load the location, the memory contents of location at 1004 hex into register R1. The reason this works is because register 2 contains the value 1, and then we shift left by 2 bits, it becomes the value of 4. Added to R3, this gives us the location 1004 hex. Now R3 is unchanged by the operation given in this instruction. The next instruction is to store value in R0 into address location 1004 hex. So consequently, we combine R3 with R2 and LSL #2 to access the address location 1004 hex. And finally, we store R1 into address 1000 hex by just using R3 by itself. Next, we look at how we can use swap to perform a similar operation. Now in this case, we would take note that the value in certain registers are unknown at the beginning. Alright, this is indicated by the question mark in the example comments. The first statement, swap R1 R0 #R3, will load the value in memory address location 1000 hex into R1, and now memory address location 1000 hex has the contents of R0, which we do not know the value of at this moment. The next instruction, swap R0 R1 open square bracket R3, #4, now accesses the address location 1004 hex and load that into R0. Alright, and then the contents of R1 is now stored into address location 1004 hex, which actually was from originally from address location 1000 hex. Okay. The third instruction would be to swap R1, R0 square bracket R3, which then stores the value in R1 from address location 1004 hex into address location 1000 hex. So consequently, at the end of these three instructions, we will have swapped the contents of memory location 1000 hex with the memory location of 1004 hex. We realize that we actually only need one register to perform the swap operation. In this case, the first step is to swap R0, R3, which loads the address location 1000 hex, the contents of this address location, into register R0. Then we will store the contents of this register R0 into address location 1004 hex using the next swap instruction. And finally, the new contents of register R0, which came from address location 1004 hex, we will store back into address location 1000. This will again achieve the purpose of swapping memory contents from 1000 to 1004 and vice versa. Finally, at the end of this manipulation, we would like to restore the contents of the registers to the original values. This is achieved by using the load multiple full descending stack statement, which given here is LDMFD stack pointer exclamation comma R0 dash R3. This will load registers R0, R1, R2, R3 from memory back into their original registers, and the stack pointer is updated to indicate that those variables have been removed from the stack. We will now focus our attention on the integer arithmetic instructions. These are the addition, subtraction, multiplication, as well as equivalent instructions for multiplication and division. First, addition instructions. There are two versions: addition, which is ADD, and addition with carry, which is ADC instruction. Now, these two instructions have the same format. Both instructions have an optional S suffix to indicate updates of the status flag registers. The first instruction, add, will take the value in R sub n added with the expression of operand 2, and the result of it will be placed into destination register R sub d. The second version, add with carry, is similar except that the addition includes the value of the carry flag C. So if carry has 1, then the result will be incremented by 1 from the typical add result. If carry is 0, it is identical to ADD itself. Subtraction is similar. There is subtract SUB and subtraction with borrow or SBC. Borrow is actually the same as the carry in terms of the flag that is used. The difference is that the carry occurs when you add two values in the register and it exceeds the size of the result exceeds the size of the original register. For example, if you add 8-bit value to 8-bit value, 255 add with 1, you get 256. But it doesn't fit in 8 bits, it now has to occupy 9 bits. Now in a 32-bit register, if you add two numbers and the result exceeds the size of 32 bits, the extra bit or most significant bit will become the carry. Conversely, for subtraction, if you subtract two numbers and the first number is smaller than the second number, you need to perform a borrow to come up with the result. And so the borrow will be captured in the carry flag of the status register. So these two instructions allow us to perform the subtraction using the borrow to handle values that are greater than the size of a given register. Now there is a different version of subtraction called reverse subtraction and reverse subtraction with borrow. The difference is that it swaps the position of operand 2 and R sub n. So in the case of reverse subtraction or RSB, the result is given by operand 2 minus R sub n. And reverse subtract with carry is operand 2 minus R sub n minus the inverse of the carry flag. Multiplication is often performed inside a program. In the ARM processor, it provides two versions of the multiplication instruction. One is the multiply with 32-bit results, the other one is the multiply with the 64-bit results. Now the multiply instruction is not strictly a RISC processor instruction. It's actually an instruction that takes multiple cycles to execute. Now, the MUL instruction or multiply instruction takes the results, the two operands R sub m and R sub s, and the result of the multiplication is stored into R sub d as a 32-bit value. Of course, if the size exceeds the size of R sub d, we will get an overflow. Now the alternative version, which is called the MUL long or multiply long, will take R sub m and R sub s and store the result in R sub d low and R sub d high, which are two different registers that you can specify. So this 64-bit value contains the upper part of the 64-bit value and the lower part of the 64-bit value in two separate registers. Now we can perform signed and unsigned multiplications. This is indicated by the S MULL for signed multiplication and the U MULL for unsigned long multiplication. Now another operation commonly found in digital signal processing is the multiply with accumulate. So this instruction MLA, multiply and add, is very useful in a processor and is provided by the ARM processor architecture as a convenience. Similar to the MUL instructions, we have MLA and an XMLAL or multiply and accumulate long, which handles 32-bit and 64-bit results. There is a special class of multiplication requirements which involves multiplication by powers of 2. if we have a value that's multiplied by 2, 4, 8, 16, or some other multiples of 2, powers of 2, we can use a different form of a multiplication. This uses the shift left instruction as operand 2 option to perform the multiplication. Consequently, if we do MOV RD, R sub n, LSL hash I, this will allow us to convert the value R sub n into a value that is multiplied by 2 sub power of I. And it is equivalent to the instruction LSL, or logical shift left, RD, Rn, hash I. We can perform multiplications by 2 power of I plus 1 or 2 power of I minus 1 by using the add version of the instruction, which is add RD, Rn, LSL hash 1, which multiplies R sub n by 2 power of I, and then added to that 2 power n itself, which gives us a multiplication by 2 power of I plus 1. The value of multiplication of 2Rn by 2 powers I minus 1 is accomplished by using the reverse subtract operation, RSB, RD, Rn, LSL hash I. We can also implement a simple multiply and accumulate instruction involving powers of 2 by using the add RD, Rn, LSL hash I instruction format. This allows us to multiply a value by 2 power of I, and then add to that a different value stored in R sub m. Now, there are no dedicated division instructions in the ARM architecture. Divisions often have to be implemented as algorithms or subroutines. However, for a special class of division problems involving powers of 2 as the divisors, we can then implement it using move RD, Rn, ASR hash I, which is arithmetic shift right, by I bits. This will divide the value in R sub n by 2 power of I, and the result, or the quotient, will be stored into R sub d. Okay, the equivalent instruction to this is ASR RD, Rn hash I. The next group of instructions are the logic instructions. Logic instructions are similar to the arithmetic instructions, except that the operation is performed bit by bit, meaning that the value of R sub n is operated upon with the value in operand 2, specified in operand 2, in a bit by bit position, starting from bit 0, bit 1, bit 2, all the way to bit 31, and the result stored in RD. So the various logical operations that we can perform is OR, which is a bitwise OR, meaning that 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1, and 1 or 1 is 1. Okay? And performs a bitwise AND, which requires both Rn and operand 2 values in the register to be both 1 to result in a 1 bit in the destination register. Exclusive OR is the bitwise operation, which will result in a 1 value in RD if only one of Rn or operand 2 has a bit value of 1. If both of them have the same value, then it becomes a result bit value of 0. A move negative is actually a NOT operation, which inverts or once complement the value in operand 2 to be stored into the destination register. Finally, we have a bit clear instruction, which masks the value in Rn using the operand 2 register value, so that all values, all bits in operand 2 that are set to 1 will be cleared in result register RD. The remaining bits in Rn that are not corresponding to bits that are set in operand 2 will be unchanged. So if you have a bit mask or bit map in memory which is stored in a register, we can use the following instructions for performing bit manipulations. If you would like to clear a given number of bits in the register, we use operand 2 as a bit mask and use the bit clear or BIC instruction. If you want to set those bits, we will use the ORR instructions and operand 2 as a bit mask. And finally, if you would like to toggle the bits in the register, we will use the exclusive OR instruction using operand 2 as a bit mask. Here we see some examples of logical instructions in use. First example, ORR R0 R1 hash OXFF will initialize the least significant 8 bits of R1 to 1, and the result will be stored into R0 with R1 unchanged. Second example, MVN R0 hash 0x00 will invert the constant value of 0, which gives you a 1's complement value of FFFF, all bits are 1 in the register, and store it into R0. This is equivalent to a -1 sign 2's complement value. Third instruction, ORR R7 R7 OX00 80000000 will set bit 23 in register 7 to 1. Since the source register and the destination are the same, this will modify R7 to have bit 23 set. The next instruction, MVN R3, R0 will take the value in R0, perform 1's complement, meaning invert all the bits in R0, and then store the result into R3. Finally, AND R3, R2, R0, LSL hash 3 will take the value in R0 multiplied by 8, because logical shift left by 3 is multiplied by 2 power of 3, which is 8, and using that as a mask, perform a bitwise AND on R2, and the result will be stored into R3. Now after the end of this instruction, R2 and R0 are unchanged. Next we look at shift and rotates, which are actually part of the operand 2 expression specification. Logical shift left will insert 0 bits from the right into the register, and the bits on the left will be shifted into the carry depending on the number of bits that we are shifted by. The converse case, logical shift right will insert 0 bits from the most significant bit on the left, and the least significant bit will be shifted into the carry flag on the right. There is a version of shift right, which is arithmetic shift right, which preserves the sign bit, meaning that the most significant bit, or bit 31, will maintain this value regardless of the number of bits that are shifted to the right. This is important because when you're dealing with signed numbers, we do not want to change a negative number into a positive number, or vice versa. Now rotate right will take the bits from the register and permutate it to the right, such that the least significant bit will come in on the most significant bit, and everything is shifted right to compensate. Now rotate right will also copy the least significant bit into the carry flag. There is no rotate left instruction or version of the shift and rotate instruction. Instead, we can implement rotate left by I bits by doing a rotate right by 32 minus I number of bits. Finally, there is a rotate right extended, which includes the carry bit as a 33-bit rotation. As I mentioned previously, shift and rotate instructions are actually built into the arithmetic logic unit, or ALU. There are two versions of where there is a variable shift and rotate, and there's a fixed or constant specified shift and rotate version of the instruction. There are no dedicated instructions for shift and rotate. Instead, it is part of the MOV instructions. So for example, you have move RD, RM, LSL, whether you have RS or else a constant value specified as a number of bits to shift. Okay. If we use a unified assembly language syntax from ARM, it will look like the following: LSL, LSR, ASR, ROR, and RX is specified directly as an instruction mnemonic instead of using the MOV with operand 2 format. The next group of instructions are called the comparison instructions. Comparison instructions will always update the condition flags. Therefore, there is no S suffix for comparison instructions. Now, in this case, a compare instruction, a CMP, will compare the value in R sub n with the operand 2 expression and set the flags in the processor status register accordingly. No result is stored as part of the compare instruction. The compare negative actually performs a 2's complement on the operand 2 and then subtract it from R sub n. So it's actually equivalent to Rn plus operand 2. Now there is a test equivalent operation which performs an exclusive OR between Rn and operand 2. And if all the bits are similar, then the value will be equal. Now, it does not affect the overflow flag, unlike the other instructions. The test instruction, on the other hand, will perform an AND operation between R sub n and operand 2. Again, it does not affect the overflow flag or the V flag. So what are the condition flags again? We have the negative flag, which is set based on bit 31 of the most significant bit value, or else known as a signed bit. We have a zero flag, which is set if the result is 0 or the comparison is equal. We have the carry flag, which is set if the addition exceeded the register range, or else the subtraction resulted in a borrow. In addition, as mentioned previously, the rotate and shift operations will also update the carry flag where appropriate. Finally, the overflow flag is set if the sign has changed after the sign addition or subtraction operation. Here again, we look at the conditional execution suffixes that is used for performing conditional execution as well as branch operations. Here we have the equal, not equal conditions. We have the higher or higher and same, or else the lower and lower and same, as well as the greater than equal, lower than and lower and equal conditions. Now bear in mind that one group of conditions are used for signed numbers or signed comparisons. The other group are used for unsigned comparisons. You must use the correct comparison for the given input values, whether signed or unsigned. The ARM processor has a unique feature of having conditional execution of all ARM state instructions. What this means is that any instruction can be suffixed with a conditional code, and the instruction is only executed if the condition is satisfied. Otherwise, it's a no operation, meaning that the register states and the flag's status are unchanged. So this gives fixed execution time regardless of the conditions of the inputs and processing requirements. This simplifies the timing or the execution timing of a certain algorithm. Examples of conditional execution are as follows. Add lower than R1, R2, R3 will only store the result of R2 plus R3 into R1 if the earlier comparison or other condition flags have been updated to have the state of lower than. The move not equal R0, R2 will only store value of R2 into register R0 if earlier there has been a status flag update that causes it to indicate a not equal condition. Finally, a subtract if equal R4, R7, and R8 will only store the result of R7 minus R8 into R4 if an earlier comparison or some other instruction causes the flags to indicate that it is equal. We make use of all these conditional execution statements for flow control. So examples of flow control instructions are the branch or B instruction. Typically, we use it with a conditional execution suffix to allow us to take a branch in a depending on the value of certain inputs. A branch and link instruction is used to call a subroutine. The branch and exchange instruction is a special instruction to switch between ARM and thumb states of execution. We will cover this in greater detail when we study the thumb state later. Finally, the supervisor or SVC instruction is actually a exception instruction that allows us to switch to supervisor mode for processing by the kernel program. The SWI mnemonic was the old syntax or the software interrupt mnemonic. This is equivalent to SVC, but the assembler will recognize both SVC and SWI as equivalent instructions. We will now see how we can use these conditional branch instructions for decision making. Example of conditional branch instructions in high-level languages such as C are if, then, else, switch, while, do, while, and for. We will study the case of the if, then, else construct. This is a fragment of instructions in pseudocode which says load button press status, which is a boolean value, into R0. If the value in R0 is true, meaning it's non-zero, then branch to statement location pressed. Okay. Else, we load value in memory address location 4000 hex into register R1. There may be other instructions in between which we were not interested in. We will now look at how we will implement this in ARM assembly language. Now the comments here indicate the pseudocode as we presented in the earlier slide. Here we see the definition of a variable in memory. This is accessed or achieved by using the .data statement, which is an assembly directive to indicate the allocation of memory locations. The .align 4 indicates that the data in memory should be aligned to a word boundary. It's important for word size access because the microprocessor or microcontroller will have a page fault if we try to access a non-word aligned memory location. Then we define the variable button press, which is defined as a word or 32-bit value having a constant initialized value of 0, 1 constant. In the beginning of this program, we will load the memory address location for button press into register R1 for use as a pointer. Then we will load the value in memory into R0 using R1 as the pointer address given in the second instruction, load R0, square bracket R1. Now we see the operation of the if then else construct. Compare R0 hash 0 will compare against 0 such that we can set the flags in the status register. Now based on this comparison, we will perform a conditional branch. Branch will not equal pressed, meaning that if the value in R0 is non-zero, meaning it is not equal to 0, we will then jump to the pressed condition or statement. Otherwise, if the value in R0 is equal to 0, we would then load the constant value 4000 hex into R1 and we retrieve from memory address 4000 hex the value in memory into register R1. Now please note that this instruction LDR R1, hash R1 will replace the pointer address with the contents of our memory location 4000 hex. With that, we come to the end of part 1. In part 2, we'll look at how we can apply what you have learned to solve a simple problem in robotics, which is to follow a line painted on the ground. See you next time.